Hello and welcome to this lecture on the design of power transmission systems. As we discussed earlier, in a power transmission system there are many different components. One of the most important components in such a system are the gears that we select. In fact, if we ask ourselves, what are the limitations on transmitting a certain amount of horsepower in a given power transmission system? Well, this is what we would like to discuss today, is that we'll find that the limitation on transmitting horsepower is going to be the design of the teeth for each one of the gears involved. In other words, the strength of the gear in static conditions and in dynamic conditions and under fatigue and during contact with other teeth. Such strength considerations will be important because they will determine how much power one can transmit. So we're going to present here a way to compute the stresses in gears, and once we do that, we will just develop analytical formulation that is known as the Lewis formula for bending of gear teeth. We will discover that such a formulation is just a very rough approximation to what's happening, and therefore to address many of the different practical considerations in gear design, we will switch over to what is known as the AGMA method for gear design. And the AGMA is the American Gear Manufacturing Association, in which many of the environmental and material factors are included in an empirical way. So there will be a lot of factors that we have to be cognizant with when we make the design for the gears. So let's first start with the motivation, the basic idea, the Lewis formula, and then move on to the AGMA method. So in this case, if we consider a gear, the tooth of a gear it can look like this. So it has a face and then a front and a flank, as you can see here. So we can look at the profile that is produced by an envelope process that looks like this. And if we look at the geometry, we're going to just kind of make a little approximation here. We will consider that we have a center line like here, and that center line we can make a tangent to the root of the gear, and this tangent, once we have a tangent point, from the tangent point to the corresponding tangent point, this will be the width of the gear tooth. And if we take a normal here, this normal will meet at a distance x below the root of the gear. So if we define distances, this is the thickness t, and the height of the tooth is L, down to, let me just be a little bit more careful, so it's down to the root right here. And the tooth itself will have a face width that is very important, and this face width is going to be denoted by F. So the geometry has F and has L and has T. So Lewis was the first one to propose a simple method to calculate the stresses on a tooth. If we look at the effect of power transmission, the transmitted force Wt is tangential, and it causes a moment and the moment is about the base that is equal to Wt times L. Now, Lewis thought that a useful approximation would be to consider the tooth as a simple beam, and basically it's approximated in this fashion. So if we have the width is f, let me see, put f here as the width. So we have f here, and thickness is t, and height is L. So the bending stress sigma is equal to the moment divided by the second moment of area divided by c, which is the distance from the neutral axis to the top surface. So if we just have the cross section, then this is the distance c is here, and the maximum stress will be on this face or the other face. I, as we know, is bh cubed over 12, and the b in this case is f, and the h is the t, and therefore this is the second moment of area. C is t over 2. So if we plug that in, we'll find that we have the bending stress is equal to Wt times L over f t squared, and then we have a 6 here. So that would be basically Lewis formula for bending. However, we just are going to do a little bit of manipulations here. So if we go back to try to understand the relationships, we have a small triangle here, if you look at it, and it is similar to this large triangle. The similarity shows us that x divided by t over 2 is equal to t over 2 divided by L. So this particular similarity gives us a relationship that allows us to proceed further and manipulate this equation. So if we have this relationship, then we can use it to write that t squared over 4L, t squared over 4L is equal to x. And that allows us to rewrite the bending stress as 3W tangential. Let me just make the t as a super, and the L will be eliminated because t squared over L here will be eliminated as 4x, so it will be 3 over 2 times f times x. So this is a simpler relationship. And now if we would like to get this in terms of the pitch, so we're going to multiply top and bottom by the circular pitch, and also if we take x over p and let that be equal to y, in other words, y is a fractional distance, so it's a distance x divided by the circular pitch, then we find that the sigma in this case is equal to Wt. Well, actually we can absorb also the 2/3 in here, so that would make it even simpler. So Wt over f times y times p. And furthermore, if we multiply by pi, divide by pi, and we know that p over pi is equal to 1 over the diametral pitch, then finally, and then we redefine y times lowercase pi times lowercase y as capital Y, then we have now finally this important relationship that sigma is the tangential component of the force times the diametral pitch divided by the face width times this factor y, and this factor y is basically called the Lewis factor. So that's kind of the relationship that we were trying to derive, and it is going to be the basis for calculations of the stresses in beams. So this is as far as we can go in terms of an analytical formulation for the bending stress. And as you see this equation that you have here on the board, if you know the diametral pitch, and so that comes from the gear spec, and the transmitted force that comes from the horsepower, because the horsepower you can convert it to a torque, and the torque you can convert it to a tangential force. So if you know these quantities and you know the face width F, which is 3 times, let's say, the circular pitch, then you'll be able to compute the bending stress once we know this Lewis factor. As you can see, the Lewis factor is a geometry factor. So in reality, it has to be computed and stored ahead of time. So that's what we have here, is that the Lewis factor is, in fact, here's the derivation, and here's the final equation that we have, is that sigma is given as W tangential times P over F times Y. And the Lewis factor is a pure geometry factor, as you can see here. So it is xp over 2/3 of xp over 3. So if you measure x and p from the geometry, then you can determine that for each gear. And that has been determined. So it depends on the number of teeth. The smallest number of teeth you have almost like a quarter, and the largest number of teeth you have almost like a half. So it goes to the rack situation, or several hundred teeth, then the Lewis factor goes to half. So if we have a small number of teeth, the Lewis factor is small, and therefore the stress is high. If we have a large number of teeth, the Lewis factor is large, and then the stress is going to be lower by a factor of 2 at most. Now, this situation is for static loading. However, if we have dynamic effects, and the dynamic effects are related to how fast we apply the loading, and it depends on critically on the pitch line velocity, V, in foot per minute. So experimental evidence and correlations indicated that we can absorb that factor and the pitch line velocity effect into a dynamic factor case of V, and this case of V is 600 plus V over 600 for cast iron, and then it becomes less important as you go for cut or milled profile and so forth. So you have these correlations to determine the pitch line velocity effects on the dynamic factor. So if you look now, finally, we have one formula in US customary units that gives us the stress in bending stress, the Lewis formula, in which we have the product of the tangential force and the diametral pitch divided by the face size F and the Lewis factor. And in order for us to include dynamic effects, we multiply that by K sub V. So you notice that there is essentially two empirical factors in this equation. And these two empirical factors are the K sub V and the Y. So we need to know K sub V and Y. And in this, if we apply Lewis equations, these two are known. We have an equation for K sub V and a table for the Lewis factor. So there's no problem with that. However, in real practice, if you go and work in the industry, and some of you are going to be working actually to develop and design a power transmission system, then you need to follow much more detailed rules that have been set by the American Gear Association, AGMA, American Gear Manufacturing Association. So the two factors that we have, the K sub V and the Y, are going to be much more involved and have a number of other correlations. And that's what I'm going to show you now is the AGMA method after we take this example. So in this example, we have a design problem in which we have an RPM that is specified, and we wanted to determine the corresponding the horsepower rating of the gear system. In other words, we have a gear, so we have selected the gear already, we know what it is, and we know that we want to run it at 1200 RPM. Question is that what is the maximum horsepower that can be transmitted? Okay, so there's a limitation there. So as you can see here, we have the diametral pitch is 8 teeth per inch, and F is 1.5, and the gear has 16 teeth and a pressure angle of 20. And the material is given, and we need to design it for a factor of safety of 3. And we want to rate the horsepower output of the gear corresponding to 1200 RPM. So the steps in this process are the following. First, we need to find the pitch line velocity in foot per minute. And once we have the pitch line velocity in foot per minute, we need to find the maximum force, the tangential force that can be transmitted to any tooth in this gear based on the Lewis formula and the strength of the material and the safety factor. So once we know that WT, then the product of this force WT times the pitch line velocity is going to be the maximum allowable horsepower. That's what we have here. So the pitch line velocity is 2 pi Rn or pi dn. In every revolution n, you get a pi d length, and that's in inch per minute. And if you divide by 12, you get it in foot per minute. So we have 628 foot per minute. And the velocity factor is given because the steel is good steel, 1020 steel. So you have a velocity factor of 1.5. Once we know that, then we can rewrite the equation that we had before. Remember that sigma was equal to WT K sub V P divided by Fy. Then we can solve it backwards, knowing that the allowable strength is 10,000 from the data, and the data comes from the IC 1020 steel, gives us the allowable strength to be 10,000. So because we have the ultimate strength is 55 and the yield strength is 30, and when we have a design factor of 3, meaning that we divide 30 by 3, you get an allowable strength of 10. So once we have the allowable strength of 10, then you see that the tangential transmitted force cannot exceed 365 pounds, which means that the horsepower is the force times the velocity, and this is a conversion factor, 32,000. So if you put the right units, you get 6.95 horsepower. So that's kind of a simplified example that shows us that we can, in fact, get a relationship between the transmitted horsepower and the gear configuration, which means size and the number of teeth involved, and the width of the face of each tooth. So in this case, there's this kind of relationship that must be examined if we are designing a power transmission system. So that's kind of the whole idea behind the relationship. Now I'm going to just go quickly over the AGMA method because it's more empirical, but I'm going to make some comments on the factors involved. And for those of you who are going to be designing real systems, then you need to use the AGMA method in the design with the appropriate factors involved. So the AGMA method is based on the stress is equal to, this is the bending stress. So we look at the bending stress first. So it's equal to the tangential force times the diametral pitch divided by the face width. Remember, before we had two factors. We had the K sub V and we had a geometry factor Y. So this geometry factor Y is replaced by another geometry factor J for the bending stress. We will comment on the US customer units, and for SI units it's a similar equation with slightly different symbols in which the module replaces the diametral pitch because it's the inverse. So let's just focus on the US customer units. So in this case, we find that there are additional factors that must be considered. One is for overload, and one for size, and one for load distribution on the tooth face, and one for called the rim factor. In other words, if I divide them up, so this is kind of loading related to the loading. This is related to the geometry of the tooth. So in other words, instead of the Y, we have this group of factors, and instead of the K sub V, we have two additional factors in here. So we have overload factor, dynamic factor, size factor, and we have load distribution factor, rim thickness factor, in addition to the J. So if you look at it, we have 1, 2, 3, 4, 5, 6 factors in the AGMA equation that must replace the two factors in the Lewis equation. For contact stress, as we know, that there is very strong contact between teeth, and when we have this strong contact at contact points, then it would be like a contact stress, and the contact stress is like a Hertzian type stress. And the Hertzian stress, we have equations for it. We can estimate Hertzian contact stress from knowing the elastic constants of each one of the contacting objects. If they're different, of course, it will be different because we have a pinion and we have a gear. And also, if they have surface effects, like surfaces are hardened differently, then we must consider those. And that's basically a different type of stress that also must be computed and designed for. So we have to design for bending, and we have to design for contact. So the AGMA contact stress has 1, 2, 3, 4, 5, 6, 7 factors. So the three factors, K, overload, velocity, and size are the same. Load distribution factor is the same. So now we have a C sub P and C sub F and an I. So if you look at this, C sub P is an elastic coefficient, which one would expect from elastic moduli E1 and E2 if you have two different elastic moduli as a Hertzian contact problem. And C sub F depends on the condition of the surface, how it is hardened. And I is a geometry factor for pitting resistance, very similar to the J, replacing the J. So with that, we can determine these stresses if we know all of these factors. Now, in order for us to gauge if the stresses have reached some limit, we must relate the stress computed in bending to the allowable in bending, and also the stress computed in contact to the allowable in contact. And AGMA has very specific rules in how to compute the strength of the material, how to convert the original strength of the material, which is S ultimate to S yield, how to convert that to an allowable using additional factors that are empirical as well. So the idea here is that you have allowable stress numbers and strength rather than the strength are used in this case. And the way it is expressed is that you have an allowable bending stress, which we use directly in the Lewis equation, but here we're going to be more careful because we have a safety factor. So you divide the allowable bending stress by the safety factor. And in addition to that, we can, in essence, include cyclic effects in this factor y sub n. So it is like an Sn type factor, like for fatigue. And we have a reliability factor Kr and a temperature factor Kt, depending on the temperature that is used. So to summarize, from S sub T is the original. Then we have a safety factor. We have a fatigue factor. We have a temperature factor. We have a reliability factor. And those are the ones that we use. In the case of a contact stress, so we have an allowable contact stress and a safety factor, and in addition to that, we also have similar stress cycle factor and hardness ratio factor, so an additional one, and the temperature factor and the reliability factor as well. So what I would like you now to do is kind of think about it as a design problem. So there's really just a familiarity with the factors that are used and applying them for a particular design. In Shigley's book, there's all of the correlations are shown, and in some cases the correlations are given in either tabular form or in a graphical form. So basically what we need to do for the design is to use these correlations. If they are given as equations, we can always program them in MATLAB or just solve them analytically. Or if they're given as graphical, we could use the graphs of the tables directly, whichever is more convenient for the design. So I'll just gloss over that part just to show you how they look like and what they depend on, and then go directly to the finish line where we're going to have an example on gear design using the AGMA method. So the factors here, this is the geometry factor, is related to the Lewis factor. So here's the original Lewis factor that we had, which we have a table for, and now we have additional values for the load sharing ratio, and that's given by here. And then we can determine the J factor for the AGMA equation, which is shown to us here graphically. Now the next one is the pitting resistant geometry factor for contact, which is similar to the J, and this is given analytically, depends on the pressure angle and the gear ratio, and that can be computed analytically from here. The elastic coefficient factor is obtained essentially from the Hertzian contact problem that we looked at earlier in the first few lectures. So you can see that the elastic modulus of the gear and the pinion and the Poisson's ratios are given here. And that is very simple to calculate. If one doesn't want to calculate it and you know the material directly with the elastic modulus, then you can use it. You can find it directly from here. The dynamic factor depends on what is known as a quality number, and the quality number for the gear from 3 to 7 is commercial quality. From 8 to 12 is precision, very high precision. So that can add to the cost, of course. And then when we do the selection for the gear, we have to consider the cost as also a factor in the design, and that comes in here in the quality factor Q sub V. And that is given, so the simple form of K sub V that we used in the Lewis equation has two parameters, A and B, in addition to the pitch line velocity. And the A and the B depend, especially the B, depends on the quality factor being the lowest is 3. So anything above 3 will be obtained. And we have a maximum velocity for a given quality number anyway. These are shown here. And then we have the overload factor, and the overload factor is the following idea. If I have a source of power like a motor, and then I have the driven machine, so how do I operate the source of power and the driven machine? Do I turn the source of power slowly, or do I just boom, turn it on in a shock mode? And how do I absorb that energy? Do I kind of absorb it slowly in the system, or is it absorbed in a shock mode? Obviously, the larger the shock, then the more like you have a dynamic force that is amplifying the static normal stresses that we've been calculating. So the overload factor depends on the driven machine versus the power source. And you have a matrix here: uniform, moderate shock, heavy shock. So if you have heavy and medium shock here, the maximum is 2.25 increase in the effective loading. Surface condition factor accounts for any detrimental effects on surface finish, and we don't have values for AGMA. So this is usually we use 1, but there might be specific cases in your design that you have to find it in exact. The size factor is the inverse of the Marin factor B, and is given in a formula here. So it's very much related to the fatigue Marin size factor K sub B that we talked about before. The load distribution factor depends on how uniform the load is, and here the load distribution factor is given in terms of a number of parameters, CMC, CPF, and that is a geometry. You can see the only factor here is the geometry, the face width of the tooth, and C sub E depends on the condition exactly. So this is the load distribution factor. Tells you how the load is distributed without doing very detailed finite element calculations because designers would like to just do a quick calculation. The load distribution factor also has this factor CPM. So the CPM depends on the mounting. So if you have bearings that are very close to the gear, is different from bearings that are very far. So it depends on S1 over S. So it depends on this distance divided by S. One can have either 1 or 1.5. So if SL over S is long, so you would expect the load to be a little bit heavier. So you'll correct for that distance from the mount. It's given also in tables here. And if you look at the hardness ratio factor, this is when we have contact between the gears. The hardness ratio factor is taken as 1 for the pinion because the pinion is usually hardened more than the gear. And therefore, for the gear, you compute the hardness ratio factor. It depends on the Brinell hardness value for the pinion and the Brinell hardness value for the gear, and is given in graphs in here. The stress cycle factors, if we have fatigue, usually the gears are designed for 10 to the 7 or higher number of cycles, and those are given in figures. So we have Y sub n and Y sub n for bending, Z sub n for contact stress. We have them in figure 1414 is like an SN curve. So depending on the hardness of the material and depending on the number of cycles that are required, then we can compute a particular value for the stress cycle factor, and we are given these types of equations to describe the curve, very similar to what we've done in the SN analysis, and the same thing for contact stresses. Finally, the reliability factor is given in equation form, empirical equation form, and given in a table that if we are content with a reliability of 50%, we take that factor to be 0.7. If we want very high reliability, then we take the factor to be 1.5. Temperature factor is 1 if we have lower temperatures. If we are operating at high temperature, then we have to ratio the yield strength at different temperatures to obtain that factor. Now, if we have a very long, kind of very wide diameter, but the rim is thin, then if you have a force on the tooth, then the tooth is going to bend even more. So there's like the support here is very important. If the support is small, then you can get an additional bending effect. And that's the idea here of the rim thickness factor, K sub B. So it depends on thickness of the rim. So if we have a solid gear or a gear that has a thicker rim in relationship to the height of the tooth, then we expect that this factor to be 1, as in here. But if the rim is thin, then we have to add additional, it's like the bending effect becomes even larger, and then we use an enhancement of that factor, as you can see from the figure. The factors of safety, now we can compute them backwards. In other words, we used to have sigma allowable. So if we have the bending stress and the fully corrected bending strength, which is the S sub t times the cycle factor over the temperature factor and the reliability factor. Once you make the corrections with those, then you can compute the safety factor for bending or for contact in here. So once we do that, I think we have now the ingredients to make a gear design based on the AGMA method. So what we will do now is we get a kind of a quick review of the bending and contact stress calculations using AGMA procedure, and then we'll just finish it with a practical example. So if you see here, the procedure is that once we know the number of teeth of the gear and the diametral pitch, we can find the diameter of the gear. Once we know the diameter of the gear, then we can use it to calculate the pitch line velocity in foot per minute. Once we know the pitch line velocity, we would be able to also know the tangential force that is transmitted in here, and the tangential force now is used to estimate the gear bending stress. So then the tangential force times P over F is the main three variables, but then we have now these 6 equations: K overload, velocity, shape, load distribution factor, and rim bending factor, and the geometry factor, and we have all of the equations necessary to compute that. Then we have to go to, so this is a stress, then we have to find the strength, the allowable. So the allowable is S sub T, which is at 10 to the 7 cycles. What is the allowable strength of the material from the tables, and what is the safety factor required, and now the cycle factor, and the temperature, and the reliability factor. And finally, we get a bending factor of safety consistent with the transmitted power. Same thing must be also done for surface wear of the gear teeth. Same procedure, but different variables, and we have complete equations to make these evaluations. So let's stop here at this point to now recap that we will be able to make a design, and we'll take a short break, and then we'll come back and look at a full example on the relationship between the transmitted horsepower and the gear configuration and material.